begin. Amos will be here today, so I'm going to replace him. It's my honor to introduce Professor Roee Ozeri from the Weizmann Institute. Roee did his PhD in the Weizmann Institute with Neil Davidson on Bose-Einstein condensation and measuring renewable excitations. DC. Then he moved to Boulder to work with Nobel laureate Dave Weinland, where he worked on ion traps, social component information. And then he returned to the Weizmann Institute in 2007, where he built the first ion trap experiment in Israel, working on quantum information. Then in 2009, he started a second experiment, which I think he will mainly focus on in his talk today, which is an experiment in which he looks on interaction between atom and ions. And since this year, he has a third experiment where he is looking for physics beyond the standard model using AR mode techniques. So this is very interesting. So I have to invite you at least 2 times more to hear about the other experiments. All of that is very important, but that's not the most important thing you should know about Roee. Roee is a VIP since a week ago, right?
And I have, so I'm going to give you a spoiler. We didn't get our kashrut document at the end because we were not sticking to the religious rules sufficiently. Even though, and that's not, it doesn't show up here, and I tried to get the picture, but I failed to do it quickly enough. We got a blessing to our lab, so it's carved into a big chamsa, and it's now hanging by the side of the door, so it wasn't broadcast. But our lab is officially blessed, so from now on I expect all experiments to move forward easier and more quickly. So thank you very much for the invitation. It's always a pleasure being here and seeing so many friendly faces. In fact, Yoav mentioned I did my PhD on measuring Ugu excitations. That was together with Jeff, many hours in the lab, and I overlapped with Yoav as well and many of you, so it's a pleasure being here and thanks for the invitation. What I'd like to tell you about today is an experiment we started working on in 2009, and it took us quite a bit of time, almost 6 years to get to the point where we can actually measure stuff. And in this experiment, what we do is we take a single trapped ion, what you see here, this red dot here, sorry, it's the fluorescence image of a single trapped ion, and we immerse it in a gas of anywhere between 10 to the 4 and 10 to the 5 rubidium atoms at a temperature of about a microkelvin or a few microkelvin. This is not a quantum degenerate gas, this is a thermal gas of atoms. We keep the density low so the collision rate between the ion and the atoms would be at the kilohertz rate, so we can still measure things on time scales where we can monitor a single up to a few collisions. What we're studying with this picture is the ultracold interactions between this ion and these atoms. And that's what I want to tell you about today. So, since the development of laser cooling techniques at the end of the 70s and early 80s, there was a lot of development in the field that people have created ensembles of ultra-cold atoms or ions and have been able to demonstrate many, many fabulous or spectacular things with them. I think trapped ions, the main forte or the main strength of trapped ions is that the coherent control available on arrays of trapped ions, what you see here is an image, again a fluorescence image of 8 single trapped ions in our lab, is phenomenal. And people have been able to demonstrate a universal set of quantum gates and therefore perform quantum computing protocols on such arrays. People have built the best, or at least some of the best, atomic clocks today that can measure, if you like, gravitational redshifts over centimeters. People have been able to perform extremely precise measurements using these trapped ions. Neutral atoms have also shown spectacular progress. In neutral atoms, usually people work with ensembles of atoms. So sometimes people work with 1 or 2 or 3 atoms, but I think most experiments use ensembles of a million or a few million or up to 10 to the 9 cold atoms where interactions play a very dominant role. So people have been studying Bose-Einstein condensates. This is the famous picture of the first condensate that was achieved in, I believe, in Gila, Colorado. This is the correct image. People have been working on Fermi-degenerate gases, similar to what Yoav is doing here. People have been studying superfluidity, both in Bose-Einstein condensates as well as Fermi-degenerate gases. People are now studying bipolar gases. People have been studying a lot of analogies to the physics that happens in condensed matter systems, similar to superfluid quantum insulator, phase transition. This is a very rich system, and it's very finely tuned. If you think about it a little bit, these two systems are very different from one another. In trapped ions, there is a very strong 1/r Coulomb repulsion between them. That's the reason they freeze into these Wigner crystals. These are, oops. There we go. These ions are trapped in electromagnetic traps. They have a very strong confining potential around them. They're very cold, and because they repel each other, they freeze into these Wigner crystals. Because of the very strong interaction, there is no overlap between their wave functions. And that's why statistics doesn't play any role here. It doesn't matter whether these are fermions or bosons, you're basically going to get the same physics. They're separated by micrometers. Their interaction, if you like, is classical. The Coulomb interaction between them is really classical. There's nothing quantum about it. The quantum nature of this system is actually in the phonons, or the little vibrations that you get in this crystal. Normal modes, vibrations can be quantized, cooled to a ground state, and then non-classical states of motion can be generated. The atomic structure of these guys plays pretty much no role in their interaction. In fact, if you want to measure dipolar interactions between these guys, that's quite a challenge. It's actually something we've done in our group, but the interaction strength between them, because of the large separation, is in the millihertz range, if you like. So it's very difficult to probe, and it doesn't play much role in the interaction between them. Neutral atoms, on the other hand, are very different. The interaction between them is short range. Most of the system studied is dominated by the van der Waals interaction, which decays as -1/6. Physics happens at very short distances. It happens when the two electronic wave functions overlaps. And therefore, quantum statistics is very important. You're going to get very different physics if you're talking about bosons, and you'll see Bose-Einstein condensation and similar phenomena, where you're talking about fermions, where Fermi pressure would dominate the physics that you're looking at. You can cool them down sufficiently to get to the S-wave scattering regime. This is a scattering regime where there's basically a single parameter that governs their interaction. And the atomic structure has everything to do with their interaction, whether they have strong dipole moments, strong quadrupole moments. The physics is going to look very different. So these are two very different systems. And since people have been investigating these systems for very long times and able to get interesting and impactful results, about a decade ago, people started thinking of the physics that you would get when you would combine these two highly controllable systems and try to study the interaction between them. What I've listed here is a list of all the atom-ion experiments that at least I'm aware of today. You can see that throughout the last decade, I think the first experimental results were around 2009. Both at the Vuletich group at MIT, studying ytterbium plus mixture, as well as an experiment by Michael Cole's group back then at Cambridge, studying ytterbium plus rubidium mixtures. Since then, the number of experiments have grown quite significantly. There are actually two sort of classes of experiments that people do with these systems. One type of experiment relies on overlapping magneto-optical traps, which is sort of the workhorse of laser cooling. If you like, these magneto-optical traps generate ensembles of up to 1 billion atoms, but they're at temperatures that are in the range of 1 millikelvin or so, and they're not in their ground electronic state. They're always excited by the presence of light. So all these black-colored experiments listed here rely on magneto-optic traps, and about half the experiment are geared, or at least trying to drive towards the microkelvin energy regime. And when you do that, you cannot use at least not at the stage where the ion and the atoms are interacting. What you use are conservative potentials, similar to either magnetic or optical traps, where the atoms can be evaporatively cooled, similar to what Jeff or Yoav are doing, to microkelvin temperatures, and only then you overlap the ion with them. So that's the two types of experiments that people do. How about the interaction scale when you look at a single ion interacting with atoms? As I said, when you look at atom-atom interactions, they repel each other via the Coulomb potential. It's a very strong 1/r repulsion. This interaction, for all practical purposes, can be considered classical. Neutral atoms, most species that people study are van der Waals interaction that decays minus 1/r to the 6th. In this case, the interaction can be modeled efficiently as a delta function at the origin of the center of mass. So you can model the interaction as a contact interaction, and therefore you can cool down and work in the S-wave scattering regime. People are now studying dipolar gases where you have two permanent dipoles interacting with each other. This interaction is non-isotropic. It can actually not be modeled by a delta function potential. So you cannot go to the S-wave scattering regime, and there's a lot of rich and interesting physics. Ion-atom interaction is modeled as minus 1/r to the 4th potential, which is the last stop before long range. So minus 1/r to the 4th potential is the last scaling law of interaction potentials that you can still model as a delta function at the origin of the center of mass. So it's sort of at the border of being fully long range. It's easy to understand why you get minus 1/r to the 4th potential. The interaction, or the long-range part of the interaction between an ion and a neutral atom, is due to the fact that the ion electric field, Coulomb field, polarizes the ion of the atom. It creates a dipole moment, and then the field and the dipole moment interact. So there's an interaction that goes like the field, scalar product of the field and the dipole moment. Now, because the dipole moment is proportional to the field, it's an induced dipole, the interaction goes as minus the field squared. And because a Coulomb field goes as 1/r squared, the interaction goes as minus 1/r to the 4th. So you have a minus 1/r to the 4th potential, and it's a much softer potential than the minus 1/r to the 6th potential that we're used to thinking of when we think of van der Waals interactions. And therefore, if we think of the potential range, and one of the ways of thinking of the potential range is trying to look for the centrifugal barrier of the first partial wave that has any angular momentum, the P wave. It's at a distance of about 1/4 of a micron from the center of origin. What does it mean? It means that in order to get to the S-wave scattering regime, in order for the scattering to be quantum mechanical, you need the de Broglie wavelength in that center of mass plane to be longer than this length scale. And that means that for typical masses, the number I'll give here is for the mixture that we use, the strontium plus and rubidium mixture, the energy that you need to be in is 18 nanokelvin. So to go down into the quantum scattering regime, you need to get to some pretty low energies. Okay? At this energy scale, the de Broglie wavelength is much longer than the potential. We can think of the potential as a delta function, and scattering really looks like scattering of a laser field from a target which has a size much smaller than the laser wavelength. So that's, in that case, scattering is isotropic. It does not depend on anything except for a single parameter, the scattering length, which tells you how strong the scattering is, if you like. But scattering is a single parameter problem and very quantum mechanical. When you go down to this quantum regime, people know that there are many, many tools which allow you to fine-tune and control these interactions. So for example, one thing people have demonstrated with ultracold atoms is the ability to use a magnetic field and tune the interaction strength, tune the cross-section, or tune the scattering length of these very cold mixtures. So what you see here is a plot of the scattering length in a mixture of two species or two spin states of fermions, and as the magnetic field is tuned across a Feshbach resonance, these fermions condense either into Bose-Einstein condensates of molecules or to a superfluid of Cooper pairs, and you observe things as exotic as Fermi superfluidity. So this is a very, very strong tool. And we aspire in these mixtures to go down to this quantum regime in order to have these tools and to be able to control and, if you like, diverge the interaction strength between this single ion and this cloud of neutral ions. And when we get there, we can do many, many things. So for example, this would be a very good system to simulate condensed matter systems. And these are just, I'm going to show just two examples. So for example, you could use the ion spin chain as a lattice and the cold atomic gas as an electron gas, as a simulator of an electron gas. The phonons in the lattice would be, the phonons in the ions would simulate the phonons in the lattice, in the condensed matter lattice, whereas the BEC, if you like, the excitations in the BEC would simulate the electron gas, and then we would couple the phonons in this ion chain to the dynamics of this ultra-cold atomic gas. We could also study these ions as small defects, so simulating small defects in metals. So for example, if you immerse a single trapped ion in an ultra-cold gas of fermions, you could start thinking about Kondo-like physics or RKKY physics, where matter wave interactions are mediated, or matter waves are mediating interactions, magnetic interactions between these trapped ions. So if we're able to take these mixtures and cool them down to the quantum regime, we think we'll have a very rich quantum system that would allow us to simulate and study many-body physics, which is similar to that of condensed matter. So what type of atoms and ions would you choose? Usually when people work with laser-cooled neutral atoms, many of the experiments are done using alkaline atoms or hydrogen-like atoms. And the reason is that these atoms have a single free electron, a single electron in the valence shell, all other electrons are frozen in quartz. And the electronic structure of these atoms is relatively simple. That means that you can use lasers to manipulate these atoms, or the electron in the atom, rather effectively. So you can laser cool them, you can detect them, you can confine them in optical potentials. It's rather easy. And for example, Jeff here is working with rubidium, Yoav is working with potassium, and many people work with choices of atoms along this column. When people work with ions, they would work with earth alkaline atoms. And the reason is that once you singly ionize them, like once you take out one electron, you're again left with an alkaline or hydrogen-like atom. So many people work with beryllium all the way down to even radium. The mixture that we chose to work is a rubidium-strontium mixture. And the unique thing about this mixture is that the masses of rubidium and strontium, of course, depending on the isotope, it's almost equal. In particular, we work with radium-87 and strontium-88, so the mass difference between them is on the 1% level. They're almost of equal mass. And that has actually very important consequences, as you'll see in a second. So I've plotted the -1/r to the fourth potential, and that's, of course, the interaction at very long range. But if we go to close range, we see that the interaction potential really depends on the details of the atom and the details of the molecule that you form when you go to small distances. So what you see here is a calculation. This is an atomic structure or molecular structure calculation of the Born-Oppenheimer potentials of the rubidium plus strontium, or strontium plus rubidium molecule. And the channel into which we use as a collision, so if you like, when we prepare our ion and atom sample, we prepare the atom, rubidium atom, in the electronic ground state, the 5s ground state, and we prepare strontium plus also in its electronic ground state. But even though we prepare both species in their ground state, we're not in the ground state of the rubidium-strontium plus molecule. In fact, there is another Born-Oppenheimer potential which lies almost 10,000 Kelvin below our preparation potential. And that is the molecular potential that, if you separate the two adiabatically, goes to rubidium plus and a neutral strontium. Now, the difference between these two is charge exchange. The electron is hopped from rubidium to strontium, neutralizing the strontium atom. This is a much lower energy configuration because rubidium plus is a noble gas. And a neutral strontium has a pair of electrons. So the electrons are paired, whereas rubidium and strontium plus are two crazy alkaline atoms with a lot of excess energy. So we're not colliding in the ground state, and this is an exothermic channel. So we can release these 10,000 Kelvin of energy and go down from this potential and undergo charge exchange and leave on this potential here. So we can either observe elastic collisions that happen here, go in and exit on this channel, or we see charge exchange collisions where we enter here but then leave here. Let's look at classical collisions for a second. So, I'm sorry, elastic collisions for a second. Classically, we can divide collisions into two types of collisions depending on the impact parameter of the collision. If the collision occurs at a higher impact than a critical impact parameter, all that happens is that in the center of mass frame, there's only a slight deflection of the trajectory of two particles, but no close contact collision occurs. Whereas, if you collide below some critical impact parameter, the two are going to spiral in until they hit each other, until a very close range contact occurs. And after that, the two separate, it's an elastic collisions, the two separate and just go in random direction. They isotropically distribute themselves in space. One particular feature of the -1 over r to the 4th potential is that the Langevin rate, the rate at which collisions, in-spiraling collisions where close contact occurs, is energy independent. And this is how you can write the Langevin rate. That means that the Langevin cross-section is proportional to 1 over the velocity. And the rate, which is equal to the density times cross-section times velocity, is energy independent. So classically, we can expect all close contact collisions with which chemistry or inelastic processes are going to be proportional to be energy independent, and we expect elastic collision to be isotropic. How do we connect this classical picture to the quantum mechanical calculation or model of collisions? Quantum mechanically, we think of the cross-section as a sum over sine square of some phase. This is a quantum mechanical phase which is acquired as the two particles slide on this molecular potential. And then we sum it with a prefactor which is proportional to the angular momentum of that collision, 1 over k squared. Now if you take this cross-section and you sum it, you perform the sum up to the maximum angular momentum which is allowed by your energy, you'll find out that you actually recover the Langevin rate up to a factor of 2. And why is there a factor of 2 there? I actually don't know. If any of you knows the answer, I'll be happy to learn it. But that's the connection that we can build between the classical picture and the quantum mechanical picture. I'm sorry, again, in the quantum mechanical picture, the semi-classical approximation says that when we have many, many partial waves, we simply replace this sine squared by a factor of 1/2. And then we get the Langevin cross-section up to a factor of 2. So if we look for quantum mechanical signatures in the scattering of atoms and ions, how will these quantum mechanical signatures look like? Here is one example. So one example would be the occurrence of shape resonances. Shape resonances are resonances that happen due to the fact that there are quasi-bound states that are confined by the centrifugal barrier of partial waves above the S, above the 0 angular momentum. Now these states are quasi-bound because they can always tunnel out through the centrifugal barrier. Now if your collision energy matches one of these quasi-bound states, the cross-section for collision enhances significantly. This is similar to, if you like, to a Fabry-Perot cavity of a matter wave. Okay? So the two particles come together, they get bound, they bounce off of each other several times, and then they tunnel out. So if you look at the cross-section as a function of energy, for sufficiently low energies, you see these nice shape resonances. So for example, if we could find these sudden increases in cross-section, that would be a quantum mechanical signature of the collision dynamics. These resonances, by the way, are rather narrow. There were a few tens of microkelvin. But I think in general, any energy dependence of the scattering or the reaction rate would already be an indication of some quantum mechanical dynamics. So before we move on to the experiments, I want to describe the machine that we have in our lab that produces these ultra-cold strontium plus rubidium mixtures. So this is a two-chamber apparatus. The system is composed out of 2 vacuum chambers. In the upper chamber, we prepare a sample of cold rubidium atoms using a magneto-optical trap. That's a standard technique. We transfer them into an optical potential where we evaporate if we cool them to microkelvin temperatures. And then we need to transfer them to a lower chamber where we have an RF cold trap, an ion trap, which I'm going to tell you a little bit in the next few minutes. So we need to transfer this coldest atomic sample 25 centimeters down into the cold trap. The way we do it is by using a technique called an optical lattice. So we take 2 laser beams, we shoot one up from the bottom, we shoot another down from the top. They interfere, so they create this one-dimensional pattern of pancakes of dark light, dark light, dark light. These pancakes of light serve as an attractive potential for the atoms, and the atoms distribute themselves over anywhere between 20 and 40 lattice sites. We then change the phase between the 2 lattice beams, and we transport these trapped atoms all the way down into the cold trap, where they interface with this with a single trap ion. In the lower chamber, we transport these atoms into another optical trap, so the density would be uniform, not modulated by the optical lattice. We let the ion and the atoms interact. As I said, the rubidium temperature is roughly 4 microkelvin. The ion is cooled to the ground state of its trapping potential, so it's also at the microkelvin temperature. The collision rate, the Langevin rate of collisions between them is at the kilohertz range. Then we turn off this optical trapping potentials. The atoms drop down. We image them with absorption imaging, so we get an image of the atoms, so we can count how many atoms we have there and what is the temperature of the atomic cloud. And then we can investigate the ion. We investigate the ion spectroscopically, and we can ask 2 things. One thing we can ask using spectroscopy is, what is the state of the ion? For example, what is the spin state of the ion? Does its spin state point in the up direction or the down direction with respect to some quantized magnetic field? And the other thing we can ask is, what is the energy of that ion? What is its energy distribution, if you like, or temperature? And the way we can measure temperature is by using the Doppler effect. So the way we know what is the temperature of the ion is by looking at its interaction with lasers that are close to resonance with 2 transitions. One transition is the transition we call an optical clock transition. It's a very narrow electric quadrupole transition at 674 nanometers. It has a natural line width of about 0.4 hertz. Our laser line width is about 50 hertz, so we get a very narrow resonance. And this transition is very sensitive to Doppler shifts, even down to the microkelvin range. The problem is that about 10 millikelvin it loses its sensitivity. It's very difficult to tell a Doppler shift of 10 millikelvin from that of 1 Kelvin, simply because this laser doesn't couple that transition any longer. The other transition we use is a very strong dipole transition. This is the same transition we use to laser cool our ion and state detect our ion. This is a transition that has a width of 20 megahertz. It starts being sensitive to Doppler shifts at the 50 millikelvin range and above. So using these 2 techniques, we can actually, and that's something we've worked on for several years, develop thermometry techniques that allow us to measure the ion temperature all the way from the microkelvin range up to the kilokelvin range. So we cover about 8 decades or 9 decades of temperature using these techniques, with one blind window which goes from about a few millikelvin all the way to a few tens of millikelvin. So we have one missing decade here that we still need to cover. So I'm going to describe 3 experiments in the remaining time. And in these experiments, I'm actually going to look at all kinds of things that the ion and the atom exchange during the collision. The first experiment is investigating elastic collisions, where the thing which is exchanged is momentum. The second experiment would be that of charge exchange, and the third would be that of spin exchange. So these 2 are inelastic type collisions. Let's start with momentum exchange. This is sort of the way a rubidium atom feels after a few microkelvin, where an ion at a few millikelvin smacks into it and really kicks it out of the trap. So elastic collisions, I mean, one naive way to think about elastic collisions in the system, we have a bath of a few tens of thousands of rubidium atoms at microkelvin temperatures. We have a single ion at millikelvin temperature, and what you would expect is for the ion to thermalize, to collide with these atoms, exchange momentum, and eventually thermalize at their own temperature at the microkelvin range. So that's the naive picture, but it's not necessarily what happens. And the reason is that when we trap the ion, we don't trap the ion in a regular conservative potential. The potential that we use is an RF potential. We use a linear pole trap. And the way the pole trap traps the ions, and the reason you can't trap charged particles in 3 dimensions. In 3 dimensions is due to the Laplace equation. The sum of the second order derivatives of the electrostatic potential has been null, so I cannot use a static potential to trap the ion. The potential that I use is an RF potential. It oscillates at a very fast frequency, and it provides radial confinement, which is effective. Okay, so the way the ion is trapped is by feeling the RF fields oscillating at fast frequencies. In our case, it's a couple of tens of megahertz, and being driven away from the high RF amplitude to the center of the trap where the amplitude nulls. So if you look at the distribution of RF fields around the trap center, you see that it's 0, or at least at a minimum in the center, and then increases linearly as we go away from the trap center. Axially, along this soft direction, we trap the ion with electrostatic fields, and in one dimension we can do it. So if we look at the ion motion as a function of time, it really looks something like this. We have harmonic motion in this pseudo-potential, but imposed on this harmonic motion, there's a very, very fast micromotion that happens at the RF frequency. So the question we're really asking is, how does this momentum exchange, and you can take sympathetic cooling as an example, work in the case where the ion has some driven component of motion at the RF frequency? And when you have collisions under a drive, you're not necessarily cooling. And it's actually quite easy to see why. Let's take a driven particle which oscillates around a velocity of 0. So its temperature, if you like, is 0, but it's still driven between some plus maximal velocity and minus maximal velocity. And let's imagine that in this one-dimensional problem, the ion collides with another particle which has an equal mass and instantaneously loses all its velocity. Now when it does that, if the collision happened at the maximum velocity, and the velocity happens to be 0, now the drive starts from here, and the average velocity is no longer 0. So if we think of the average velocity, or the thermal velocity of that particle, it actually increased. Whereas if the velocity occurred at the 0 crossing, then you're not going to get any heating at all. So this type of dynamics can introduce heating as well as cooling. In the pole trap itself, there's a very nice geometrical way of understanding the dynamics of collisions with atoms. If I just look at the trajectory of a particle which is harmonically bound, its trajectory in phase space is going to look something like this. So this is not a pole trap. This is just a particle which is bound in a one-dimensional harmonic potential. If that particle collides with an equal mass particle and instantaneously loses its velocity, you're going to map its trajectory onto an ellipse which would always be smaller, which means that that particle always cooled down. And if collisions would keep on occurring, eventually that particle would cool down to a halt if it collides with zero energy particles. So in this case, the particle energy would be determined by the back energy. If you look at the phase space of an ion trapped in a cold trap, the phase space trajectory looks much more complicated. It looks something like this. But it's actually rather easy to understand this complicated phase space trajectory. If I now take snapshots of the ion trajectory at the same phase of RF, I recover at the phase of 0, I recover the harmonic oscillator ellipse. And at other phases, I'm going to get ellipses which are tilted and a little bit stretched. Now what would happen, so if I just take this ellipse and wobble it at the RF frequency, I'm going to recover this complicated phase space trajectory. Now what happens when I collide? When I collide with the atoms, it really depends on which phase of the RF I collided. If I collided at a moment where the phase of the RF was equal either 0 or pi, that looks like collisions in a simple harmonic potential. That means that I'll always get cooling. However, if I collide at an RF phase which equals pi over 2 or 3 pi over 2, I'm going to collide at this very tilted ellipse, which means that if I lose my velocity instantaneously, I can either cool down if I collide close to the center of the trap, but I can also significantly heat up. In fact, a collision can either take all my energy or double my energy. And we've actually investigated this experimentally. What you see here is the distribution of energies of an ion which is heated axially in the direction where there's no RF. We let the ion collide for about 1.4 collisions, and we see that these collisions always cool down the ion. We always get collisions of smaller energy. Whereas if we heat the ion up radially in the direction where there is RF fields and there is micromotions, we see events in which the ion has doubled its energy. And that leads, so by now what I've talked about is single collision events and the energy that you can get after a single collision. What would be the energy distribution that you get when the ion keeps on colliding with the atoms? Now remember that the RF amplitude as we go away from the trap center keeps on increasing. So if you like, the collisional dynamics here looks like an all-in casino. Okay, the ion in a single collision can lose all its money or double its money, double its energy. When it doubles its energy, it can excur even further out into the RF field. Again, the next collision can either lose all its energy or double its energy, which means that what you have here, the energy of the ion would be a random variable which is proportional to a product of all the collision energies rather than a sum. Now if you have a random variable which is the sum of many random variables, you always get a normal distribution. But if you get a random variable which is proportional to the product of many random variables, you recover these power law distributions. And the statistics that describe these, yes?
The masses are identical, almost identical, right?
I'm sorry,
the
masses are identical, yes, almost identical.
How do you get to the point where all the energy is transferred and just be half or something like that?
Well, that's like identical billiard balls, right? You transfer all, when the masses are identical, that's when you transfer your velocities. If you would collide with an infinite mass thing, it's like colliding with a wall. Your velocity just goes to the minus velocity. Whereas if you collide with an identical mass, that's like the Newton cradle, if you like.
So this statement, you don't average over all angles or something like that.
You don't, I'm sorry?
You don't average over all directions or something like that.
Well, this is a 3D. Well, in the case of a head-on collision, you would lose all the energy. Of course, in 3 dimensions, you don't necessarily lose your energy. But if you look at in one collision, you can either lose all your energy or double all your energy and anything in between. Right? So you can actually cover it.
It's 1D.
No, it's not a 1D. This is a 3D problem. So if we look at the energy distribution that we get, eventually we get a power law distribution. which can, for example, be described by Tsali statistics. So this Tsali's distribution of energies here is a generalization of a thermal distribution. It has two parameters in there. One parameter would be T, which is, if you like, the mode. It's proportional to the most probable energy, to the peak of the distribution. And another parameter called M, which would determine the power law of that distribution. The power law depends on the trap parameters. The power law also very much depends on the ion to atom mass ratio. If the ion and the atom masses are the same, N here equals 4, which means that the energy distribution, taking into account this density of states factor here, goes down like 1 over E squared, okay, which is a pretty radical power law distribution.
This is the distribution of what?
This is the distribution of ion energies after, if you like, its steady state, after it has collided many times with the atoms.
So what's that steady state? There should be some dissipation.
Well, the dissipation is the collision with the atoms. The collision with the atoms cool you down, but they can also heat you up.
You're assuming that the atoms are just a fixed temperature or fixed?
Yes, so what I'm assuming here is that I have an ensemble of, let's say, 10 to the 5 atoms. It's a microcanonical ensemble. I don't dissipate them anymore. They're at a temperature of a few microkelvin. Every time the ion collides with one of the atoms, that atom goes away from the trap. So it doesn't change the atomic, the temperature of the atomic bath. And this process goes on, let's say, for 1,000 collisions. So the number of atoms that I lost is negligible, but the ion has already reached some steady state. It's not thermal equilibrium. This is not a thermal equilibrium type scenario, because there's always energy being pumped in. Coupled in with using collisions from the RF fields into the trap. Right, in the end going to infinity limit, this distribution would converge to be the usual thermal distribution. So this Tsali's function can describe anything from thermal all the way to very radical parallel distributions. The 1 over E squared distribution, for example, doesn't have an average. Right? It's still a distribution, you can normalize it, but it has no average. So this type of dynamics has been studied theoretically for a few theoretical works, and what people have shown is that, I should say, the tail of the energy source doesn't depend, or the power law doesn't depend much on the details of the system. So it doesn't matter if there are other, the atomic temperature is this or that, or there's some imperfections in the trap that prevent the RF field from being 0 at the center. The tail always does not depend on the details of interaction, but the bulk, the maximum temperature here certainly depends on these details. So one could ask the following question. One could say, if you would use 0 temperature atoms and your trap would have been perfect, what would be the steady state of that distribution in terms of the parameters that you use, both N and T? What would be the steady state temperature, if you like? And like in all-in casino, there's only one fixed point. The only fixed point which is there is that where you lost all your money and then you can't gamble anymore, right? So we can always hope that eventually we'll have one collision that would bring the ion to a halt, and then this process would stop, right? We'll go bankrupt, using the casino analogy. But you could also ask yourself, okay, this system is quantum mechanical. There's a wave function to that ground state ion, and that does overlap some RF field. So eventually, there's always some non-zero RF amplitude that the ion would see. And in this proposal, which dates to 2012, the people from Vlad Vulic's group at MIT suggested that the limiting mechanism would be the following. During a collision, the atom and ion approach each other. The minus 1 over r to the 4th potential is an attractive potential. It will pull the ion away from the trap center into finite RF regions, and that finite RF field would set the limit to the minimal temperature that you would get. So we set ourselves to measure this dynamics, and the experiment we did, we cooled the ion to the ground state of the trap. We used atoms that were in the microkelvin range, so for all practical purposes they had 0 temperature. and we observed the dynamics. And what we saw was that as a function of time, if I look at the Thales distribution here, the power law slowly evolved, and after about 10 collisions settled to be n equal 4, which means that the energy distribution decays as 1 over E squared. Again, a pretty radical distribution without any average. And T, this, the temperature of the ions slowly heats up as a function of time. And if we compare our experimental results to the model that I've shown before, or a simulation that includes the model that we've shown before, where the atom approaches the trap center and pulls the ion away into finite RF fields, we see a rather good agreement. So this dynamics tells us that trying to measure microkelvin temperatures with equal masses atom-ion mixtures is rather hopeless. The ion pretty quickly, over the course of a few tens of collisions, heats up to the millikelvin scale. If we investigate the dynamics that occurs at the very first collision, we can still try and nail down microkelvin time dynamics. But this is really the, if you like, the limit to the temperatures, the lower limit to the temperatures that are attainable in these ion-neutral mixtures, at least when you use a pole trap in order to trap the ion. How much time do I have? About 5 minutes? Okay, so I'm going to quickly try to cover charge exchange and spin exchange. I'll leave as a teaser, if you like. So charge exchange is the following process. We let the two guys, the ion and the neutral atom, collide. Energy has to be released. So this is an exothermic process. So for example, a photon can be emitted, and then rubidium atom turns into a rubidium ion. It becomes trapped in the trap. The strontium ion becomes a neutral strontium and then drifts away. And the way we see it is then if we trap two strontium plus ions, we see that one of them disappears, but we know that there's still an ion in there because the guy on the right side did not jump into the trap center. So we know there's a dark ion there. And we can measure the mass of this dark ion by measuring the normal mode structure of this two-ion crystal. And we see the shift of the mechanical resonance frequency indicating a shift in the mass. And from this spectral shift, we can actually tell that this is a rubidium plus ion. So I can show you the way we can measure, for example, the time constant over which this dynamics happens is to put, in this case, it's 8 ions in the trap, and you see that as times go by, more and more of them become dark. And the reason you know they're there is that when ions hop from one place to the other, you can still see these dark ions stick around. If we measure, charge exchange can happen in various ways. This energy can be released radiatively by the emission of a photon. It can be released through three-body recombination, and it can also be released by some non-adiabatic potential crossing. By measuring the dependence of this reaction on the density of atoms, we see a linear dependence, which means that this is a two-body process, which is very likely to be radiative. And when we measure the dependence of this charge exchange on energy, we see that the dependence, we don't see the expected Langevin dependence, which is energy independent, but rather a rather sharp dependence on energy, which indicates that this is not a classical process per se. I'm not going to go over spin exchange, but I will mention one thing, and is that when we immerse the ion in a spin-polarized bath of atoms, we see that collisions polarize the ion spin along with the direction of the atomic path spin. So spin exchange collisions collisionally pump the spin of the ion to align with that of the atomic path around it. Now when we do that, we can actually play with the spin symmetry of the two electrons of the rubidium and the strontium plus. When the two electrons are parallel, they're symmetric under exchange, and that means we're only overlapping the triplet, spin triplet part of the molecular potential. Whereas if the two spins are non-parallel, we can also populate the spin singlet collisional manifold. Now because the ground state of the molecule after undergoing charge exchange is a singlet, we cannot go this reaction if we start in the triplet potential. And therefore, by controlling the spin of the atomic bath, we could actually control the charge exchange reaction rate. We can control the rate at which the electron jumps from rubidium into strontium plus. So that's a nice demonstration of spin control of an ion-neutral chemical reaction, if you like. Okay, so I'm going to let you go after I do 3 more things. One is to sum up and to tell you that I've shown you a couple of experiments investigating ultra-cold ion-neutral mixtures. We plan on to continue to study both spin dynamics, non-equilibrium dynamics. One experiment in particular that we're pushing forward now is to study the optical clock transition of the ion in the presence of atoms, looking for frequency shifts and signatures of the dynamics of the collision on this very narrow optical clock transition. We're going to search for quantum signatures in collisions. I think we've already seen a glimpse of that, seeing an energy-dependent, if you like, charge exchange rate. In the future, we would like to have it go colder, but as we see, using cold traps, we cannot do that. So one way of perhaps going to colder temperatures would be to use optical trapping for the ion. So similar to the trap for the neutral atoms, a similar type of trap would be able to trap the ion as well. Another possible direction of studying stronger interactions would be to try and dress the atoms with a Rydberg excitation and therefore turn them into a much softer dipole and then have a very strong ion-neutral interaction rate. The next thing I want to do is actually acknowledge and thank, so I've been describing this work but not doing this work, the heroes who actually did this work. This is a non-trivial experiment that combines 2 rather complicated experimental techniques. So Ziv Meir and Yoni Dalal were the first PhD students who embarked on this project of building this system. Thomas Sikorski later joined Udi Ben Shlomi, Merav Pinkas, and Nitzan Ackerman are also part of this effort. Studying ultra-cold ion-neutral interactions is only one thing we do. In our group, we also have another all-ion effort, which is geared towards implementing quantum information processing. In particular, we're interested in methods to actively combat decoherence, so decoherence-free subspaces, quantum error correction codes, dynamic decoupling. What you see here is a universal set of gates on each 2 or single ions in a 3-ion register. You can push that up to about 7 or 8 ions. We've been using these protocols also for the purpose of quantum metrology and enhancing the precision with which measurements can be done. And as Yoav mentioned, we're now working on a setup that would use these precision tests in order to search for new physics beyond the standard model. What you see here is the output of a collaboration with the high energy theory group, Gilad Perez, Yotam Sorek, and Cedric Delaunay, where we propose to use the measurement of isotope shifts in narrow optical clock transitions in order to search for new scalar Higgs-like forces that have not been discovered so far. And with that, I'd like to end and thank all the members of the ion trapping group and our funding agencies. Thanks.
Okay, so some questions.
Charge exchange depends only on orbital quantum numbers. You prepare your sample specific L state, or do you have a handle with the radial decay on what it was?
So you're talking about the L states of the collision or the L states of the electron within the atom?
The electron within the atom.
So with the electron within the atom, we actually prepare ourselves in the s orbital. So we prepare ourselves in the s orbital of both these guys. But when they move in, you start mixing with other levels.
Right,
of
primarily
course.
at higher levels. Do you have any handle on how those decay?
I mean,
Just
this.
down to
Well, the density dependence tells us it's radiative. So if it's non-radiative and it's a two-body process, that means that either there was some Landau-Zenner transition and the energy was released into kinetic energy, and then you would see the ion heating up. So we don't see the ion heating up. Or there would be some molecular formation, and then we would see that as well. We would see the mass now is not rubidium plus, but rather rubidium strontium plus, so that's twice the mass. So by the fact that we have two-body interactions and the fact that we don't see any energy release or molecular formation, we can tell that it's radiating. In terms of the angular momentum of the two ions colliding, we control that with the temperature to the best of our ability. So if the collision occurs at a millikelvin energy, there are about 20 partial waves. So L goes all the way up to continuously.
And one question.
Oh, sorry. You increase the frequency of the RF of the call trap for lower temperature.
Well, if we increase the frequency of the RF, I think the effect on the energy distribution is going to be marginal. It's not going to be very large. If we could decrease the RF amplitude, that would have a significant effect on maintaining low temperatures. The problem is if you go below a certain RF amplitude, you lose the ion, you lose stability. So I think eventually we'll have to actually, adiabatically go to electrostatic trapping.
Okay, I just thought that the frequency, as the frequency goes higher, it's a better and better trap. The effective potential becomes less and less effective, more and more like a real. It's just a guess.
That's true, although the collision itself, the Lange-Van collision itself, is rather fast. It happens at a few picosecond time scale. So as long as the RF frequency is slow as compared with that, I think it will be very difficult for us to go the gigahertz range. The potential is, the collision is instantaneous within the RF phase. I think it's an interesting question to ask what would happen when the RF phase would vary during the collision, during the time over which the ion had to exchange momentum, but I think we're a few orders of magnitude away from that.
Maybe I can ask a quick question. So you showed the charges change, and you said that you can see the dark ion, the rubidium. How comes if so much energy is released, you can actually still track this rubidium ion? Where does it absorb some of the energy?
So two things. One is that the energy is released through a photon. So it doesn't heat up. In fact, it remains cold. The other thing to keep in mind is that these pole traps have a depth of about a few eV, which means they're tens of thousands of Kelvin deep. So very differently from the neutral traps, which are micro-Kelvin deep, to lose an ion, you really need to release a lot of energy.
Okay, no more questions.